Hello everyone. Today we will study about the topic ionic equilibrium in detail, and this is part 1. Let's start. Disclaimer, which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the images. This is our index slide, and these are the major topics which we will going to see and which we will going to study today in detail. First one, weak and strong electrolytes, ionization of electrolytes, degree of dissociation or ionization, Ostwald's dilution law, various concepts of acids and bases and their ionization, relative strength of monoacidic bases, ionization of water, and then we will conclude by the summary slide. Let's move to the first topic, which is weak and strong electrolytes. So there are two types of electrolytes, weak electrolytes and strong electrolytes. First of all, we are studying ionic equilibrium. So the equilibrium concept also extends to ionic reactions. There are ionic reactions in which ions are involved, in which the molecule is having ionic bonds. There it is known as ionic equilibrium and applied as equilibrium between dissociated and undissociated form of an ionic reaction of weak acid, weak base, hydrolysis reaction, etc. So we will going to talk about the ionic equilibrium in detail. So we have two type of electrolytes, weak electrolytes and strong electrolytes. What are weak electrolytes? They dissociate partially in the solution, and such solutions are poor conductor of electricity. So the electrolytes which dissociate partially in the solution, not completely, are to be known as weak electrolytes, and their characteristic is that they are poor conductor of electricity. They do not conduct electricity. The example of weak electrolytes are CH3COOH, acetic acid, CH3COH, H3PO4, H3BO3, NH4OH, or HCN. These are some examples of weak electrolytes. Uh, they dissociate partially in the solution. Dissociating means dividing into the ions, or or a compound we have CH3COH. On dissolving it into the water or any solution, it dissociates into CH3CO minus and H plus. Right. So they did not dissociate completely because CH3CO is still a bounded ion. It can be separated like CH3 plus and CO minus, but no, it is combinedly dissociate as CH3CO minus, and H plus will be released from this. So these are weak electrolytes. Other than that, the strong electrolytes is opposite of weak electrolytes. They dissociate completely into their ions in the solution, and such solutions are very good conductor of electricity. So one of the property of the strong electrolytes that they conduct electricity, and the solution of strong electrolytes conduct electricity or a very good conductor of electricity. The example of strong electrolytes are HCl, H2SO4, NaOH, KOH, NaCl, KCl, etc. These are some examples for the strong electrolytes, right? Let's move on. Ionization of electrolytes. So we have our electrolytes. It has its types like weak and strong. But how the ionization of electrolytes occur? So separation of an electrolyte into their ions, either on fusion or dissolution, is called ionization or dissociation. So basically, when an electrolyte separate into their ions, either on the fusion or on dissolution, is called ionization or dissociation. Fusion means two things are combining, making a single thing. Dissolution means one thing is dissociating into two things, right? So Separation of an electrolyte into ions is known as ionization or dissociation, depends upon the nature, whether the electrolyte is in the fusion process or the dissolution. For example, NaCl in the aqueous solution gives us Na positive and Cl negative ions. So this is dissociation reaction. Usually, the term dissociation is used for weak electrolyte and ionization for strong electrolyte. This is a point to remember, that the term dissociation, usually it is observed that the dissociation term is used for weak electrolytes, whereas the ionization is used for strong electrolytes. You can also say that in the weak electrolyte dissociation happens, and in the strong electrolytes ionization happens. The solution of weak electrolytes contains ions which are in equilibrium with unionized molecules. So the solution in which weak electrolytes is present, they are at equilibrium with and the equilibrium is between the ions and the unionized molecule. For example, let's take this one, like this acetic acid is dissociating into CH3COO minus plus H plus, right? So this is a dissociation because we are using a weak electrolyte first of all. Then you can see that in the solution of weak electrolyte, equilibrium is established. This double arrow means this reaction is in equilibrium, and the equilibrium is between the unionized molecule and the ions. Second reaction, second example, NH4OH dissociating into NH4 positive plus OH minus, and there is also a equilibrium between the ions and the unionized molecule. This equilibrium is known as ionic equilibrium and is dynamic in nature. So this equilibrium which is establishing here in these two examples we have seen, this type of equilibrium is known as ionic equilibrium, as it is happening between ions and unionized molecule, and it is dynamic in the nature. Let's see the definition of degree of dissociation or ionization. So under ionic equilibrium, the degree of dissociation and ionization is an important term. So the fraction of total number of moles undergoing ionization is called degree of ionization or dissociation, represented by alpha. So by how much fraction, by how much amount the total number of moles undergoing ionization is known as degree of ionization or dissociation. Depends whether ionization is happening or dissociation is happening. Alternatively, the fraction of the amount of an electrolyte present in the solution as free ions is called degree of ionization. It is also represented by alpha. So alpha, you can write the formula of alpha in this way, that number of moles of electrolyte dissociated ionized as ions divided by total number of moles of electrolyte dissolved. Okay, by using this we can calculate the alpha. The extent of ionization depends upon the strength of bond and extent of solution of ions obtained. So the extent of ionization, how much ionization is happening, it is depends upon the bond strength in which the molecule is present, for which the molecule is present and the molecule is undergoing dissociation. So for that particular molecule, what is the bond strength of that molecule and what is the extent of solution of ions which is obtained after dissolution? They are the factors on which the ionization or extent of ionization depends upon. Various factors influencing degree of ionization or dissociation are as follows. So what other than this influence the degree of ionization or dissolution? So first is, for a strong electrolyte, alpha is considered as 1 at normal dilution, while for most of the polar covalent compounds, that is weak electrolytes. For the weak electrolytes, alpha is very, very less than 1. these are the two things we have to remember, that for the strong electrolyte, alpha is equals to 1. For weak electrolytes, alpha is very, very less than 1. Okay. Now, second factor, degree of ionization of an electrolyte increases with polarity of solvent. So, as the polarity of the solvent increases, the degree of ionization of an electrolyte also increases. Third factor, the degree of ionization of an electrolyte decreases with increase in concentration of the electrolyte. So, if we increase the concentration of electrolyte, the degree of ionization will decrease. Fourth factor, the degree of ionization rises with raise in temperature of the solution. And if we raise the temperature of solution, the degree of ionization will also increases. Fifth factor, the addition of species possessing a common ion to that of weak electrolyte causes a decrease in the degree of dissociation of weak electrolytes. So if we are adding any common ion to that of weak electrolyte, it will cause a decrease in the degree of dissociation of weak electrolyte. Okay, these are some factors which will influence the degree of ionization or dissociation in a solution. Let's see the Ostwald dilution law. So what is it? So it states that degree of dissociation of weak electrolyte is inversely proportional to the square root of concentration or directly proportional to the square root of volume containing 1 mole of solute. So the degree of dissociation of weak electrolyte is inversely proportional. So this is degree of dissociation alpha. It is inversely proportional to the square root of concentration. So under root C. It is inversely proportional. So on equating it, we have to introduce the constant k. So let's suppose it is under root k. So alpha is equals to under root k by c. We can write it as alpha is equals to kv, because it is said that it is directly proportional to square root of volume. So under root kv. Because alpha is inversely related to under root c, alpha is directly related to under root v. On introducing a constant, alpha will become equal to under root k by c and under root kv. Right? And where alpha is the degree of dissociation, v is volume containing 1 mole of weak electrolyte, and k is dissociation constant. Here there is a note. Ostwald's dilution law is applicable only to weak electrolytes, because for strong electrolytes alpha is equivalent to 1, that is Ka will become infinity. Okay, so that's why the Ostwald dilution law is only applicable to the weak electrolytes, like where the dissociation term is coming, only at that place we can apply the Ostwald dilution law. Okay, this is a point to remember. Okay, let's see the various applications of Ostwald dilution law. First one, to calculate the value of dissociation constant, of course, of weak acids and weak bases by determining the degree of dissociation alpha from conductance measurement del m by del naught m at any concentration C. So we can use the Ostwald dilution law to calculate the value of dissociation constant from the degree of dissociation, and it from the degree of dissociation from the conductance measurement at any concentration C of the solution. Second application, to calculate the degree of dissociation alpha of weak acids and bases by knowing the value of K. So it is interrelated, right? So you can use the Ostwald dilution law for calculating the value of dissociation constant using alpha, using degree of dissociation. And you can also calculate degree of dissociation alpha of weak acids and bases by knowing the value of K using Ostwald dilution law. So for weak acids, put A positive is equals to H positive and K is equals to Ka. Similarly, for weak bases, B negative will be OH negative and K will be equal to Kb. This law holds good only in case of weak electrolytes. As I said, this is also mentioned in the previous slide as note that this law only holds good only to this law is only applicable for the weak electrolytes. The value of K can be calculated only in dilute solutions of weak electrolytes. Okay. Yeah. So now let's see the various concepts of acid and bases and their ionization. So an acid is that whose aqueous solution taste is sour, turns blue litmus red, neutralizes bases, and so on. There are many definitions of an acid. There can be many definitions of an acid. To define an acid, we can use many terms. So, like it tastes sour, it turns blue litmus red, it neutralizes bases, and so on. On the other hand, the aqueous solution of a base tastes bitter, turns red litmus blue, and neutralizes acid, and so on. Right? So there are some theories on the basis of concept of an acid and a base. Let's see the first one, Arrhenius theory. So what is Arrhenius theory? According to this theory, acids are substances that dissociates in water to give hydrogen ions, and bases are substances that produce hydroxyl ions, that is OH minus, in the solution. So as per the Arrhenius theory, acids are defined as the substances which produce H positive ion in dissolving into the water, and bases are the substances that produce hydroxyl ions, OH minus ions in the water. Now, there are some limitations of the Arrhenius theory, which is like free H positive and OH minus ions do not exist in water, right? Then how you can say that this is an acid and this is a base? Second, the concept is limited to aqueous solutions only. Yeah, because it says that in the aqueous solution, if a substance is producing hydrogen ion, if a substance is producing hydroxyl ions, that means that is a base, that is a acid, right? So this concept is limited to the aqueous solution. What about the other kind of solutions? Third, it cannot explain the acidic character of certain substances. And what type of certain substances? Which don't contain free H positive ions like AlCl3, BF3, and basic character of substances which don't contain free OH minus. So like NH3 and PH3. So if a substance is basic but it doesn't contain OH minus ion, then how will you explain it as a base? So this concept is also not explainable by the Arrhenius theory, and these are some limitations of this theory. Let's see another theory, which is Bronsted-Lowry concept. According to this concept, acids are proton donors while bases are protons acceptor. The first line for acids are same, like it can donate H positive, while base can accept H positive. Okay, this is according to the Bronsted-Lowry concept. A conjugate pair of acid and a base differs by a proton. The substances which behave as both as an acid and a base are called amphiprotic. Okay, so this is a term here, amphiprotic, which is used for the substances which behave both as an acid and as a base. For example, H2O, HSO3 minus, HS minus, etc. Conjugate base of weak acid is strong, or vice versa. Okay. There is a note. The strength of acid depends upon the nature of solvent. So, what is the strength of our acid? It is depend upon the nature of the solvent. For example, H2SO4, HClO4, HNO3, and HCl all have same strength in water due to the leveling effect of water. Okay, you can see here in this diagram we have introduced the concept of conjugate acid and conjugate base. So for the HCl, Cl minus and combining some other cation is a conjugate base of an acid, and for this base H2O, H3O positive is acting as a conjugate acid. Okay, so these are corresponding conjugate acid and conjugate base for the acid and base. Okay, let's see in acetic acid solvent, The order of their acidic strength is highest in the HClO4, then H2SO4, then HCl, then HNO3. And we are talking about the acetic acid solvent. So the solvent is acetic acid, and the order of the acidic strength of these four molecules are in this order. So there is also limitations to the Bronsted-Lowry concept also. So what are these? First one, the protonic definition cannot be used to explain the reactions occurring in the non-protonic solvent, right? Similarly, as we saw in the previous theory, that Arrhenius theory, that it doesn't explain the nature of the bases and acids which doesn't contain any H positive and OH minus. Similarly, in Bronsted-Lowry concept, the protonic definition cannot be used to explain the nature of an non-protect solvent like COCl2, SO2, N2 etc. Second limitation, this concept cannot explain the reaction between some acidic oxides such as CO2, SO2, SO3, and basic oxides such as calcium oxide, barium oxide, and magnesium oxide, which takes place even in the absence of solvent. For example, calcium oxide plus SO3 giving us CaSO4. Right? So the Bronsted-Lowry concept didn't explain this. Third limitation, PF3AlCl3 etc do not have any hydrogen, right? And hence cannot give a proton, but are known to behave as acids. So how the Bronsted-Lowry concept will define this? So these are some limitations for the Bronsted-Lowry concept. Okay, now let's see the third concept, that is Lewis concept. So according to this concept, acids are the substances which accept a pair of electrons to form a coordinate bond, and bases are the substances which donate a pair of electron to form a coordinate bond. Okay, so Lewis concept talks upon the concept of donating and accepting a pair of electrons by an acid or a base. And following species can act as Lewis acids, which are molecules in which central atom has incomplete octet, for example BF3, AlCl3, FeCl3, etc. So in these molecules, the central atom has incomplete octet, but they act as Lewis acids. Second, the molecules in which central atom is either non-metal, cation, or metal cation with empty d orbital. For example, SiX4, GeX4, PX3, TiCl4, H positive, Ag positive, etc. Right? So these also can act as Lewis acids as per the definition of acids given by the Lewis concept. Okay, so Lewis bases should satisfy the following conditions, and Lewis acid we have just studied that which condition should satisfy. Now Lewis bases should also satisfy these following conditions. First, octet should be complete and central atom should be more electronegative. Second, lone pair or pairs should be present on the central metal atom or the side metal atom. Okay, for example NH3. In NH3, the nitrogen is the central metal atom having a lone pair. H2O, O is having two lone pairs. ROH, O is having two lone pairs. ROR, O is having two lone pairs, etc. So they can act as Lewis bases because they can donate electrons. Third, negatively charged species like Cn minus, OH minus, Cl minus, etc. So these can also act as a Lewis bases. The limitations of Lewis concept, so the limitations is also there for the Lewis concept. So what are these? First one, the strength of Lewis acids and bases is found to be depend on the type of reaction. It is not possible to arrange them in any order of their relative strength. So as per the definition given by the Lewis concept, the strength of Lewis acids and bases is found to depend on the type of reaction it is going on, right? So it is not possible to arrange them in any order of their relative strength. We cannot arrange them in any order of their relative strength. And second limitation, it does not explain the behavior of protonic acids which do not form coordinate bond, such as HNO3, HCl, H2SO4. Right? So they donate H positive and form do a reaction, but the Lewis concept did not explain about the behavior of these type of protonic acids. Third limitation, catalytic activity of Lewis acid cannot be explained because the catalytic activity of many acids is due to their tendency to furnish H positive. So Lewis acid does not do so. It does not explain this. So these are some limitations of the Lewis concept. Okay. Now let's see the relative strength of monoacidic bases. Relative strength of monoacidic bases or monobasic acids, you can say anything, of equimolar concentrations can be given as. So concentration will be same. Strength of base BOH1 upon strength of base BOH2 will be equal to under root Kb1 upon Kb2, which is equals to alpha 1 divided by alpha 2. And strength of acid Ha1 is divided by strength of acid Ha2 is equals to under root Ka1 upon Ka2, which can be equal to alpha 1 divided by alpha 2, where the Ka and Kb are dissociation constants of acid and bases respectively. A for acid, B for bases. So these are the relative strength of monoacidic bases written in the terms of the dissociation constants of acid and bases respectively. Right? Okay. Let's see the concept of ionization of water. Pure water is a weak electrolyte and is ionized according to the following equation. This is the equation here, H2O plus H2O. It will give us H3O positive plus OH minus. Right? So this is the process of ionization of pure water. At 25 degrees Celsius, for pure water, H3O positive concentration will be equal to OH minus concentration in the product side, which is equals to 10 to the power minus 7 mole per liter. And Kw, which is called the ionic product of water, is equals to H3O positive concentration times OH minus concentration, which is nothing but equal to 10 to the power minus 14. So this is a important thing which we will use it very much. Okay, so Kw is equals to 10 to the power minus 14, and Kw is called the ionic product of water, and it is defined as product of molar concentration of H positive ions and OH minus ions. We can write the K, or you can say ionization constant can be equal to Kw, ionic product of water, divided by 55.55. Right? Okay. So value of Kw depends upon temperature, as it is equilibrium constant. And equilibrium constant is only depends on the temperature. So the value of Kw will also depends upon the temperature as it is a equilibrium constant. And if temperature increases, the value of Kw also increases. So basically it is directly related. The temperature and the equilibrium constant is directly related. One increases, another will also increase. For the dissociation of weak acids in water, Ka is called acid ionization constant. I said A for acid, right? So for the weak acids in water, Ka is acid ionization constant. So let's take this acetic acid as a weak acid plus H2O. It will dissociate into CH3COO minus plus H3O plus. The Ka, or the acid ionization constant for this, will be equal to CH3CO minus concentration times H3O plus concentration, that is product, divided by reactant, which is CH3COOH. Similarly, for a weak base, Kb is called base ionization constant. And for this reaction of a weak base NH4OH dissociating into NH4 positive and OH negative, the Kb, the base ionization constant, will be equal to the concentration of products divided by concentration of reactant. NH4 positive times OH minus divided by NH4OH. Right? So this will be the this is the thing, or this is the equation through which you can define the acid dissociation constant for a weak acid in water, and you can define the base ionization constant for a weak base in water. Okay, so we are at our summary slide, and we will cover the major topics or the major concepts which we have studied, which we have covered. So strong electrolytes completely dissociate into ions in the solution. Examples include strong acids like HCl, strong bases like NaOH, and salts like NaC. Weak electrolytes, on the other hand, only partially dissociate into ions in the solution. For example, it includes weak acids like acetic acid and weak bases like ammonia. Ionization is a process by which an electrolyte dissolves in water and splits into its constituent ions. Degree of dissociation alpha is the fraction of total number of molecules that dissociate into ions in a solution. We can count how much what is the total number of molecules that dissociate by the degree of dissociation. Ostwald's dilution law applies to weak electrolytes and states that the degree of dissociation alpha for weak electrolyte is inversely proportional to the square root of its concentration. And one more thing, directly related to the volume of the solution. Acids produced H positive ions in water, and base produce OH minus ions as per Arrhenius concept. Bronsted-Lowry concept is that acids are proton donors and bases are protons acceptors. Acids are electron pair acceptor and bases are electron pair donors, says Lewis concept. And lastly, water self-ionizes to a very small extent to form H3O positive or H positive and OH minus ions. The equilibrium constant for this process is known as ion product constant for water. These are some major concepts which we have covered in the today's lecture. Okay. Thank you.